So let's do the analysis of a transistor in saturation mode. We're saying that the EBJ and the CBJ junctions are forward biased. We know that a NPN transistor, for example, has got base, emitter, and collector. Now, the EBJ junction is forward biased means because it's a NPN transistor, so that will be the collector, the base, and the emitter. So you can think of a transistor as being made up of two diodes, basically. So in such a way that the C part, let's start with that, is of N type, which means it makes up the cathode, right? N type, and B on the other side is P type, so it's the anode of that diode. And on the other side, we've got as you go through the EBJ junction, which also has to be forward biased, but it's made up of B, which is of P type, so that will be the anode, and C, which is, E, which is of N type, so that will be the cathode of this diode. So you can think of a transistor, of an NPN transistor, like that. So to say that it operates in saturation region means that the EBJ junction is forward biased, which means the potential, a voltage of a higher potential on the base side as compared to the emitter side is applied there across that first junction, EBJ junction, and that voltage does not only have to be uh, of higher potential on the anode side with respect to the cathode side, meaning on the base side with respect to the emitter side. It also has to be higher than the barrier voltage. Remember barrier from diodes, of that specific diode making up that junction. So what that means is that VBE must be greater or equal to VB, which is normally with a silicon NPN transistor, 0.7 volt. In saturation region, the CBJ junction is also forward biased. What that means is that you also have a DC voltage which is high on this side on the base side as compared to the collector side, and that is the VBC is greater than 0, or one can see it as VCB being less than 0. Um, that way the transistor will be forward biased, and when the transistor is forward biased, both junctions of the transistor will be forward biased, which means it will be operated in saturation region. When you're in saturation region, the transistor tends to act like a closed switch. So the transistor behaves like a switch, and here we're talking about functions already. So the transistor behaves like a closed switch. It's more like its collector side was connected to the emitter side. And what that means in terms of VCE is that VCE is very small. Very small. So when you think about it, VCE is normally made up of the resistance that a transistor opposes from the collector to the emitter, and when by Ohm's law combined with the current flowing through that region, it makes up the voltage VCE. So now when the transistor behaves like a closed switch, so this is the mode in which the transistor is operated as a closed switch, you get to have a very small VCE. So for silicon-based NPN and PNP transistors, and we will notice this a bit later, we'll be operating with V saturation being 0.2 volt. But of course, that's generic for our calculations. But normally, when you read the datasheet of a specific NPN or PNP transistor, you should be able to get it predefined and assessed in the lab VCE under saturation value. The key thing is to know that it's very small. So it's very small in general. But so we'll work with VCE at saturation, at the edge of saturation, meaning when the transistor is about to go into saturation, is going into saturation, 0.2 volt. And that's what we're going to be working with to say that the transistor is in saturation. Okay, let's take a typical example. Let's say we've got an NPN transistor, which is biased as follows. We've got some resistance here of and we have another resistance here, then it's grounded here, for instance. We've got VCC here of 5 volt, for instance, and we've got a voltage VB that I can also represent this way, applied at the base of the transistor through a resistor, and this voltage happens to be 5 volt as well, for instance. Let's say this resistor here, it's the base resistor RB, and let's just say for now it's 100 ohms, just as an example. So if you do a normal DC analysis the way you learned it in electronics 1, you normally consider this loop here, and you apply Kirchhoff voltage law in that loop. And as you go through that loop, you will go with VB being equal to RB, considering that a current IB flows there, a current IE flows here, and a current IC flows here. Let's also take a RC value of about 1.2 kilo ohms, for instance. RB times the current that flows through it plus the voltage drop across the EBJ junction, which we say VBE, should be equal to VB. So RBIB plus VB should be equal to VB according to Kirchhoff's voltage law in that loop. So if we have to extract IB in here, we end up with RB being VB minus VBE over RB. So if we go with VB of 5 volt as given, it's going to be 5 VBE of 0.7 divided by RB, which is, we took RB to be 100 ohms. Actually, let's go for 1,000 ohms. And that will give 4.3 milliamps. 4.3 milliamps. So now, if one has to work out the IC value of this circuit, knowing its DC current gain beta, one will work IC as beta IB. Let's assume as well, because we didn't give it, that beta is 250, for instance, and that will be 250 times 4.3. 250 times 4.3 milliamps, which will result in this will result in, I'll just use my calculator now. We've got 4.3 milliamps times 250. Okay, that will result in a very high current of 1,075 amperes. So now, if one has to assess the VCE of this transistor, he will look at applying Kirchhoff's voltage law once more, but on this loop. As you go from VCC all the way to ground, the sum of all voltage drops must be equal to the supply voltage, which is VCC. So that will lead to VCC should be equal to RCIC plus VCE, because there's a voltage drop across RC due to IC flowing through RC as well as VCE. Now, if you extract VCE from here, one should get VCE to be VCC minus RCIC. So now, our RC is equal to our IC, is equal to 1.075 amps. So if you take 1.075 amps multiplied by the collector resistance, which we say it's 1.2, all of that, being subtracted from VCC, which is 5 volt, you end up with, let's see, 1.075 times 1.2000, which gives you, that would have given, because I'm using conditional statement now, would have given 5 minus 1, 290. This proves, which will be a negative value. So this proves that the collector current, because of course in analyzing this, we went from the assumption that the transistor is operated in active mode and do all the analysis accordingly. But as we carry on, we realize that this transistor, we can't get a VCE, which is supposed to be positive. We can't get a VCE value, And as you can see, the drop across the RC with this assumption ends up becoming too high. And this is a proof, this is a way of detecting that this transistor has already reached saturation region. So once one observes this, they should quickly realize that no, this transistor is no longer in active mode. The fact that IC is very high, it can't be in cutoff mode, because we're still going to discuss that. This transistor is definitely in saturation mode. So automatically one would go with VCE SAT. Because we are in saturation mode, you would assume that the VCE at that moment is equal to 0.2 volt about, and then you apply the same Kirchhoff's law across that loop and you end up calculating IC. So now you go VCC equals to RCIC plus VCE, and here we're talking about saturation. So now we're talking about the collector current under saturation as well. So IC under saturation will be equal to VCC minus VCE, which is 0.2 under saturation, and all of that divided by RC. So you come up with 5, a value of 5 minus 0.2 divided by 1.2, and that will give you 4.8 divided by 1.2, and that's how you get your IC under saturation. And from the IC under saturation, you can divide it by beta to work back the IB. But the fact that triggered our mind to know that we're in saturation is the fact that we first assume we're in active mode, and I will explain that more just now. And then we worked out everything and we realized that IC was too high, which led to a very big theoretical voltage drop across RC, which was exceeding the 5 volt, which is the limiting supply voltage. Then we automatically detected that we are definitely in saturation mode. That's why we went back and say, okay, we are definitely in saturation mode. IC is quite high, and in this case VC is very small. That's why the transistor behaves more like a closed switch. The other key characteristic here is that IE is therefore almost equal to IC, because the two lines are more or less touching. So now the collector and the emitter are as if they were touching. Okay, so that's why we say it behaves like a closed switch. And in this case, the VCE will be very small, which will make then the collector voltage, which is the voltage at that point, the collector voltage will become almost equal to VCC, because the collector voltage is taken from there, is measured from there to ground. VC is measured from there to ground, will be almost equal to VCC in this case. Sorry, my bad. The collector current is taken from there will be equal to 0, almost equal to 0, because it's going to be equal to VCE, which is very small. So it's going to be about 0.2 volt. So it will be as if ground has been connected to the collector. So it has been to be as if the collector has been grounded, which means the transistor behaves like a closed switch. Very important. Next to this concept is the other mode in which a transistor can be operated, which is the cutoff region or cutoff mode. Cutoff region or cutoff mode. So in this mode, the transistor behaves like a open switch. So once more, the transistor when used in this mode is operated as a switch. So the switching function is what we are using the transistor into here once more. But it's also very important to understand what will be the behavior of VCE. So for that matter, we're going to take a similar circuit to the one we just said now. We're going to have RC of 1.2 kilo ohms. We've got 5 volts, for instance. We've got RB, which is still 1 kilo ohm, basically 1000 ohms. Let's assume now a very low voltage of about, let's say, VB equals to 0.4 volt was to be applied here. So automatically the as you can see from the analysis, if you consider that loop, you realize that 0.4 is not a good number because that really at the edge. Let's just go with 0.2 volt, for instance. So if you consider that Kirchhoff voltage loop, you normally were supposed to have RB IB plus VBE to be equal to VB. Okay, but now VBE, for that to happen, the EBJ junction must be forward bias. But automatically, when VB is 0.2, and we know that we've got RB in series with a diode, so the voltage after RB will definitely be lower at that point, which is the VB at the base of the transistor actually. So basically I can call this V, yes, we call it VB1 for instance, and VB2, which is the voltage after the resistor before the before the diode or before the base of the transistor, will be less than VB1 definitely, because some of that voltage will be consumed through RB. So now that means it's gonna definitely be less than 0.2 volt. So now we know that the EBJ junction is a PN junction, and there's a PN junction, it has got a barrier voltage, which for silicon is 0.7 volt. So if you apply voltage less than 0, if we apply voltage less than 0.7 and the barrier voltage on a diode, what does it do? The diode is in reverse bias. And when the diode is in reverse bias, it doesn't conduct current through. So automatically there will be no base current. IB will be 0. And if IB is 0, that means there will be IC by default to be beta, which is beta IB, will be also 0. And if there is no collector current flowing there, then what do we observe? If IC is almost 0, that simply means that VCE on the other side, that simply means that the voltage drop across RC, which is RC IC, will also be 0, because IC is 0. And if that is the case, that means there won't be any drop there. So most of the 5 volt, for it to satisfy the Kirchhoff's voltage law in that loop, which dictates that VCC equals to VRC, which is the voltage drop across RC, plus VCE, all the if this is 0 already, that means all the VCC will be equal to VCE. In which case then, the transistor will behave like an open circuit. So VCE will be equal to VCC, will be very high. In general, will be very high. Why am I saying in general it's gonna be very high? Because in the case where there's RE, then also RE won't consume anything, because if IB is 0, IC 0, IE will be 0. So even if there was an RE there, RE times 0 will also be 0. So VCE will be equal to VCC, which will make that voltage appear here. So 5 volt will appear there, and it will look like the transistor is behaving like an open switch. You agree? That's the collector, that's the emitter, and that is the base. So it's behaving like an open switch, right? And VCC will appear here. And this is also another mode of using a transistor into a region or a mode that we call cutoff region. So those two modes are covered in electronics 1. It was just of interest to go back onto them. So there is an intermediate mode. And by the way, before we carry on, in the cutoff region, the EBJ junction is reverse biased, and as we've demonstrated, because the voltage on the base side is lower, is not higher than the barrier voltage of the diode between the base and the emitter, and the CBJ junction is also reverse biased. And that's what makes both junctions being reverse biased, we know we are in cutoff mode. The transistor operates like an open switch, very important. Now we go in the mode of our interest, which is the active mode. The active mode, this is the mode in which the transistor doesn't perform the role of a switch, but rather of an amplifier. So in this mode, the EBJ junction is forward biased, while the CBJ junction is reverse biased. So it's kind of an intermediate mode, and that's the mode we've been using in the analysis in any case. So in this mode, we've got forward bias for EBJ, and the CBJ is reverse biased. So in this mode, the transistor behaves like an amplifier. We're gonna learn how that happens just now. Thank you. We're gonna carry on just now.